When we have a conjugate pair, we can use the equation Ka times Kb equals Kw. We know Kw is 1 times 10 to the minus 14. So if we have Ka, we can rearrange the equation to solve for Kb. And if we have Kb, we can rearrange the equation to solve for Ka. Now let's take a closer look at what the equation means for the strength of conjugate acid and base pairs. If we have a strong acid, like HCl, that means the Ka will be bigger, which means the Kb of the conjugate base must be smaller. The equation shows that conjugate acid and base pairs have opposite strengths. HCl is a strong acid, and its conjugate base is super weak. If we have a strong base, the Kb will be bigger. And the Ka of the conjugate acid will be smaller. A strong base like NaOH will have a super weak conjugate acid. So the conjugates of strong acids and bases are always super weak. They react 0%, which means they don't participate in the reaction at all. We would consider them spectator ions. I listed a few examples of super weak spectator ions that include chlorine, bromine, iodine, chlorate, lithium, sodium, potassium, and calcium. Now let's look at weak acids and bases. If we have a weak acid, its conjugate base is still weak. And if we have a weak base, its conjugate acid is still weak. So the conjugates of weak acids and bases are still weak. Let's talk about how to determine the pH of salts. Salts are ionic compounds, so the first step is to dissociate the ions in the solution and cross out the spectator ions. Sometimes both ions will be spectators, which means the salt is neutral because there's nothing that will react with the water to make either H+ or OH- in the solution. But normally, only one of the ions from the salt will be a spectator that you can cross out. The other will react with the water in the solution. So the next step is to write out an equation with the remaining ion reacting with water. The products of this reaction will either include H3O+ or OH-, and that will determine whether the solution is acidic or basic. Once we know if the solution is acidic or basic, we can then determine the pH by creating an icebox and solving for the equilibrium concentration of either the H3O+ or OH-, whichever one is present. But be careful to use the correct K. So solve for Ka if the solution is acidic, and solve for Kb if it's basic. The last step is to use the concentration of either the H3O+ or OH- to solve for the pH. The first example asks if NH4Cl is acidic, basic, or neutral. If we dissociate the salt into its ions, we get NH4+ and Cl-. Cl- is a spectator ion, so cross it out and then write an equation with the remaining ion reacting with water. NH4+ donates a proton to H2O, so the products are NH3 and H3O+. The presence of H3O+ indicates that the solution will be acidic. The second example says to write out the equation for a reaction between acetic acid and lithium hydroxide. The products of the reaction are lithium acetate, which is a salt, and water. To determine whether the reaction is acidic, basic, or neutral, we'll need to dissociate the ions in the salt, cross out the spectator ion, and write an equation for the remaining ion reacting with water. Since the products of this reaction include OH-, that means the solution will be basic. The last problem asks for the pH of a 0.1 molar solution of sodium cyanide. Sodium cyanide is a salt, so dissociate its ions, cross out the spectator ion, and write an equation for the remaining ion reacting with the water in the solution. Based on the presence of OH-, we know that the solution is basic, but we'll need to create an icebox to determine the concentration of OH-. Cross out the water since it's a liquid and liquids don't affect concentration. Start with the 0.1 molar concentration of cyanide and 0 for the products. Use an unknown variable x for the change since we don't have any equilibrium concentrations we can use. And we can consider the change amount for cyanide to be negligible since we're already starting out with such a large amount of it. Now solve for x using the equilibrium expression. But remember, the solution is basic, so we'll need to use Kb. The problem gives us Ka, so use the equation we discussed earlier to solve for Kb. Then write out the equilibrium expression and solve for x. X is the equilibrium concentration of OH- in the solution. Use the concentration to solve for pOH and then solve for pH.